Hello everyone, I'm Habiba Farooq from Purdue University and I'll be presenting our work titled FaceRevelio, a face liveness detection system for smartphones with a single front camera. This is a joint work with Jahan Mohammed, Sian Sao, and Dr. Ko Wang. We all know that with more and more personal user data finding its place on smartphones, user authentication has become an absolute necessity. Several authentication mechanisms exist, like traditional password-based approaches or biometric mechanisms like iris and fingerprint scanning. Recently, face authentication has become very popular since it's easy to use and face recognition technologies have achieved good performance over the years. Now, before Apple introduced its Face ID in 2017, most face authentication systems on smartphones were based on 2D face recognition approaches. However, since then, some high-end smartphones have incorporated the 3D structure of the face into their face recognition systems. For this purpose, these phones embed specialized hardware components onto their screen. These components, although effective, occupy a notch on the screen, which is against the notch and bezel-less screen trend in the smartphone market. Some recent and upcoming smartphones are expected to get rid of this notch with only the infinity oval front camera on the screen. Additionally, many of the existing commodity smartphones lack such depth sensing hardware and therefore rely on 2D face recognition mechanisms. 2D face authentication is susceptible to 2D media, that is, photo and video spoofing attacks, where an attacker having access to photos or videos of the registered user can use these to unlock the smartphone. In order to defend against such attacks, face authentication systems usually include a liveness detection system whose job is to determine if the test subject is a real human or a spoofing attempt and allow authentication only in the case of a real human. Several liveness detection methods have been proposed previously. Some of these methods use textual features like finding the differences in degradation in HSV color space or light diffusion speed of the captured images between a live subject and a spoofing attempt, or using the differences in scale texture and dog representation of images of live and spoof subjects. The problem with these methods is that they usually rely on ideal lighting conditions and can be fooled by high-quality attack photos. Some other methods rely on some form of user interaction, such as asking the users to blink their eyes, make different facial expressions, or move the phone in a certain direction. Such user interaction is generally time-constrained and makes the system difficult to use in many scenarios, like for older people or in emergency cases. With these observations in mind, to enable secure face authentication, we aim to build a face liveness detection system which is accurate, environment independent, and does not require user interaction or specialized hardware. To achieve this goal, we introduced the idea of using smartphone screen as a light source and recording images of the face under different illumination to reconstruct the 3D surface of the face. With this core idea in mind, we built FaceRevelio, which is a face liveness detection system for smartphones with a single front camera. Here is a high-level overview of how FaceRevelio works. We begin by displaying a combination of light patterns on the smartphone screen and simultaneously record the reflection of these patterns from the user's face via the front camera. The video is passed on to an image recovery module which recovers 4 stereo images of the face, where each image represents the face illuminated under a different light source. We then use these images to compute the surface normals of the face via a computer vision technique called Photometric Stereo. Finally, a 3D model is reconstructed from these surface normals via integration and is passed on to a decision module, which analyzes depth features of the 3D model to decide if the subject is indeed a human or a spoofing attempt. Before going into the details of our system, let me first give some background about what photometric stereo is. Photometric stereo is a classic computer vision algorithm whose key idea is to utilize the fact that the amount of light that a surface reflects depends on the orientation of the surface with respect to the light source and the camera. Assuming that we have at least 3 images of the face under illumination from 3 different light sources with no other light present in the scene, and the direction of these light sources is known, we can calculate the surface normals by solving this linear system of equations. However, if we use the smartphone screen as a light source, then we don't know the direction of the light, which means we have 2 unknowns in this system. In this case, we can still approximate the surface normals by matrix factorization. So if we decompose M through SVD here, we can get L and S with an ambiguity of a 3 by 3 matrix. Here, we are just interested in the surface normals, and these surface normals can be integrated to obtain the 3D surface of the face. Now, knowing that we need to have at least 3 or more images of the face illuminated under different light sources to use photometric stereo, we realized that we can divide the smartphone screen into 4 quarters and then assume each quarter as a light source. So if we illuminate each of these quarters one by one such that at one time only one quarter is bright while the other 3 are dark, we can capture 4 images of the face illuminated by different lightings. We can then use these 4 images in photometric stereo to recover the surface normals and in turn the 3D surface of the face. Although the 3D reconstruction through this approach is good, there is one problem. If we simply illuminate each quarter of the screen one by one, anyone observing a user using our system can observe this pattern and then later record a video simulating same light sources to fool our system. So we need a method to prevent such replay attacks. In order to defend against replay attacks, we introduce the idea of a light passcode in our system. We consider that instead of illuminating each quarter separately and capturing 4 images of the face, we can record the face for a given time duration, and during that time we illuminate all 4 quarters simultaneously, but with a different random intensity value. And this random intensity value keeps changing over time. So a light passcode is basically a combination of 4 light patterns where each light pattern is a sequence of length t seconds of random numbers between -1 and 1, -1 being black and 1 being white, where at a given time instance, the random number in each pattern is set as the intensity value in its corresponding quarter on the screen. The benefit of using this light passcode is that a new random passcode is generated with each use of our system. So given the randomness involved, it's difficult for an attacker to guess what light patterns would be displayed on the screen. Once we record the video of the face, we perform a temporal correlation between the passcode extracted from the video frames and the one displayed on the screen. If a high correlation is verified, only then the system proceeds on to reconstructing the 3D surface. Now that we are illuminating all 4 quarters simultaneously, we have a problem, which is that the recorded video frames have a mixture of reflections of the 4 light patterns from the face at any point in time. Whereas in order to use photometric stereo, we need the separate impact of 4 light sources on the face as 4 stereo images. Here, a fundamental theory in optics comes in hand, which states that the intensities of incoherent lights add linearly. Based on this theory, if we choose the random intensities in each quarter to be independent of each other, we can say that the light intensity received on a certain pixel in a video frame is a weighted sum of 4 light intensities from the light passcode with a single light from each quarter illuminating the face. In other words, we can express the light received by the camera as a product of the light passcode and the face under illumination from the 4 light patterns expressed as X, which is what we need for photometric stereo. However, this model only holds if the camera response is linearly related to the light being actually reflected from the face. To ensure that this is indeed the case, we dig deeper into how modern smartphones cameras operate. And we observed that the raw camera sensor data goes through a series of operations like linearization, white balancing, demosaicing, and gamma calibration before we can see the final images on our screen. We realized that gamma calibration is the step where a nonlinear transformation is applied to the pixel values to adjust their range such that they can be displayed on normal screens or monitors. If we directly use the camera's final output, we cannot use the relationship I just mentioned. So in order to make the camera response linear, we apply an inverse gamma calibration operation to the recorded video frames, such that the camera's response linearly related to the light reflected from the face, as shown by this model. Now with this linear camera model, we can solve this system of equations to get the 4 stereo images of the face. There is still one missing piece in the puzzle. So far, we assumed that the light present in the scene is only from the smartphone screen. However, this is generally not the case since we usually use smartphones in the presence of some ambient lighting in our environment. So with ambient lighting present in the scene, the camera response will actually have a constant value representing the ambient light present in the surroundings. In order to get rid of this ambient lighting component, we design our passcode in a way that the light patterns in our passcode are all independent to each other. On top of independence, we introduce orthogonality between these 4 patterns by using Gram-Schmidt process. Gram-Schmidt process takes the 4 light patterns and generate 4 orthogonal sequences for these patterns. With this process, we ensure that a good separation exists between the impact of the 4 patterns, which will help in our stereo image recovery. Now, since our light patterns are zero mean and orthogonal, the product of passcode and ambient lighting, as well as black level of the camera, will be 0. Hence eliminated from the equation, giving us 4 stereo images without any impact of the ambient lighting. This method allows our approach to work in dark as well as in presence of ambient lighting. At this point, one might have a concern that the flashing light patterns on the screen might put some strain on the user's eye, causing some discomfort among users. So how can we make sure that our system is comfortable to use? To emphasize users' comfort, when we generate the light passcode, we apply low-pass filtering to the random lighting patterns such that their frequency is below 3 Hz. This filtering is applied before Gram-Schmidt, and since Gram-Schmidt process is linear, by induction we know that the orthogonal bases of these patterns also satisfy this frequency threshold. As you can see in the Fourier transform of the 4 patterns in the bottom row, they all have a frequency of below 3 Hz. So now, with all these steps, finally, we have 4 stereo images of the face representing illumination from 4 different light sources. Here, I'm showing the binary representation of these images where a white region in an image shows that the pixel values in this region of the image were higher than the pixel values in the same region in the other 3 images. And from this binary representation, we can see that how differently illuminated these 4 images are. With these stereo images in hand, we can finally compute the normal map as described earlier by Photometric Stereo. However, if you can recall, simply using SVD, the surface normals obtained will have an uncertainty of a 3x3 matrix. This may affect the quality of the final depth reconstruction of the face. So in order to compute the normals without this ambiguity, we designed a mesh-aware template-based approach where we use a single generalized human normal map template and align the calculated normals with this template to solve for the ambiguity matrix, and then use this matrix to find the surface normals without any ambiguity. Once we have successfully calculated the surface normals of the face, we can use these to reconstruct the 3D surface of the face using a normal integration mechanism. Here are some examples of the 3D reconstruction using our system for human subjects as well as for photographs of these 4 subjects. You can see that the 3D surface reconstructed from a human face is very different from that of a photograph. And even though the shape looks similar to a human face, which is because we use the same human normal map template in both cases, The reconstruction from the photographs lack any depth features such as areas around the nose or the mouth region. Given that there are visible differences in the reconstruction of human face and that from 2D photographs, whereas the 3D reconstruction from different humans bears similarity in depth features, instead of treating it as a classification task, we pose this problem as finding similarity between two 3D models, where instead of labeling a 3D reconstructed face as a human or a spoofing attempt, we take pairs of reconstructed models where one is from a real human while the other is our test subject, and decide if their facial depth features are similar or not. This method of training is known as one-shot learning, and it lets us increase our training data size, and our model does not need to be retrained for new users. For this purpose, we trained a deep Siamese neural network, which is based on the concept of one-shot learning, which extracts spatial depth features from the 3D reconstruction and classifies it as a human face or a spoofing attempt. The Siamese network consists of two parallel neural networks, and it takes a pair of depth maps as input, where one depth map is from a known human face, while the other one is the reconstructed face of the candidate subject. Both the parallel neural networks output a feature vector for their input depth maps, which are then compared using L1 distance and a sigmoid activation function to decide if the candidate map is indeed a human face, in which case the output is 1, or is a spoofing attempt, in which case the output is 0. Here is the design of our entire system. We perform some pre-processing on the recorded video frames and align the frames with the passcode before image recovery. The details of these steps can be found in our paper. Now let's talk about the evaluation of our system. To evaluate our system, we implemented a prototype of FaceRevelio on Samsung S10, which runs Android 9 with a 10-megapixel front camera. We invited 30 volunteers to use our system for liveness detection, and during all the experiments, we collected a high-quality image of the user to test the performance of our system against photo attacks. For the video replay attacks, we used the videos collected from real users and replayed them to our system. We evaluated the performance of our system in various lighting conditions and with different screen-to-face distances and face orientations. Our systems achieve state-of-the-art performance in detecting 2D spoofing attacks in dark, daylight, as well as indoor lighting conditions. Specifically, for dark environment, our system can detect photo attack with an accuracy of 99.7% when the real user is rejected in only 2% of the cases. For replay attacks, by finding the correlation between the passcode displayed on the screen and the camera response, our system can achieve an equal error rate of 0.15%. Our system is also robust against different screen-to-face distances and can detect spoofing attacks with a high accuracy. Similarly, the accuracy of our system is 99.3% or more for different face orientations. In terms of computation cost, on top of the signal duration of the passcode, which is 1 second in our case, our system only takes 0.13 seconds to reconstruct the face and decide if it belongs to a human or not. Therefore, in total, the computation cost of liveness detection of our system is less than 2 seconds. To summarize, by using only the front camera of a smartphone and using its screen as a light source, we can perform secure face liveness detection, which is not environment dependent or requires any user interaction. Please check out our paper for more details of our system, and thank you for watching.